The airflow speeds up as it passes over the wing and reaches its maximum speed at a certain point. The Mach number here will always be greater than that of the aircraft as a whole, called the flight Mach number. As the flight Mach number increases, so does the local Mach number at the maximum speed-up point. Eventually, though the aircraft as a whole is flying at less than the speed of sound, just at this point on the wing, the air is moving at the speed of sound. The flight Mach number when this happens is called the critical Mach number of the aircraft, usually written M crit. For any wing section, M crit will always be less than 1. As speed increases, the air does begin to show signs of compressibility. The colors show regions of increasing and decreasing density. The red area at the leading edge is the stagnation region, where the air is being slowed down and becoming denser. Immediately behind are 2 blue areas where the rate of speeding up is greatest, causing a reduction in density. This diagram will remind us of what's happening. As the flight Mach number increases, the flow at the point of maximum speed up on the wing reaches Mach 1, the speed of sound. The wing has reached its critical Mach number. And when this is exceeded, a sudden sharp region of increasing density forms on the wing just behind the point of maximum speed up. This is a shock wave. It is a sudden jump in the pressure of the air. It grows and moves back as the Mach number increases. A diagram shows what happens. At the critical Mach number, there is a point on the wing where M equals 1. At higher speeds, the point grows into an area in which the flow is supersonic. That is, where M is greater than 1. Outside this area, the flow is still subsonic. M is less than 1. The rear boundary of the area is the shock wave itself. As the aircraft accelerates, so the area of supersonic flow increases, and the shock wave moves back, growing larger and stronger. A shock wave at right angles to the airstream is the means by which the airflow suddenly decelerates from supersonic to subsonic speed. How are shock waves formed? On the rear part of the wing, every point, such as this one, sends out innumerable tiny pressure waves at the speed of sound. In the forward direction, these waves meet airflow in the opposite direction and make less and less progress until they reach a stage where they can't travel any further forward because the airflow itself is moving backwards supersonically. It's like trying to step off an escalator going the wrong way. The pressure waves constantly pile up here, and this is the shock wave. A shock wave is a very narrow region, about 1/10,000th of an inch thick. Across this region, the supersonic airflow is violently reduced to subsonic speed. Much of the air's energy of movement, or kinetic energy, is dissipated as heat. The temperature of the air rises suddenly as it passes through the shock wave. There is also a sudden rise in pressure. The energy wasted as heat in the shock wave must be continuously supplied by the engines. Otherwise, the aircraft would decelerate. So as the aircraft approaches the speed of sound, it meets an additional kind of drag called wave drag. Wave drag is a large proportion of total drag at transonic speeds. As the speed of airflow is increased still further, the region of supersonic flow goes on growing larger, and a second supersonic region starts to form on the lower surface of the wing with another shock wave. it's approaching the speed of sound, the most important result of the shock wave is to cause the airflow to separate from the wing's surface. This is called shock-induced separation. It produces a large turbulent wake which alters the pressure distribution, lift is reduced, and the turbulence creates drag. Can't see separation flush when the airflow is smooth, and flap when shock-induced separation occurs. The shock stall can also cause instability. For instance, changes in fore and aft trim. First, lift increases slightly just below the shock stall. This causes the aircraft to gain height, that is, assuming the pilot takes no correcting action. Next, at the shock stall, the sudden loss of lift puts it nose down. As the Mach number increases, the bottom shock appears and reaches the trailing edge before the top one. This forces the nose up a little. Finally, the top shock also moves to the trailing edge, making the aircraft go more nose down again. Most aircraft don't do all of these things, but the center of lift always shifts towards the rear when passing through the transonic range. So all aircraft suffer a final nose-down trim change. There is also buffeting, caused by the turbulent separated airflow from the wing striking the tailplane. Finally, the controls may lose their effectiveness. There are two main reasons for this. At subsonic speeds, a control surface affects the air all round the main surface, as the smoke streamlines show. For instance, moving an aileron affects the pressure distribution round the whole wing. But when a shock wave is present, the aileron has a much smaller effect. For any changes behind the shock wave can't affect the air ahead. Secondly, the control surface is not fully effective even behind the shock wave, for it's moving about inside a region of separated airflow, which, although turbulent, is aerodynamically dead and can't exert much force on the aircraft. But this turbulent wake can cause violent oscillations of the control surface itself. They are accompanied by large fore and aft movements of the wing shock waves. In this picture, the movements have been slowed down 40 times. These are the chief troubles which the pilot may meet when he comes up against the shock stall. But shock waves don't only appear on wings. Speed up of the airflow occurs around the canopy and many other parts of an aircraft. Wherever it's great enough, there shock waves will form. Shock waves cause a vast increase in drag and may cause serious control troubles. One way of avoiding these troubles is to put them off to still higher speeds by raising the aircraft's critical Mach number. There are two chief design methods for doing this. The first is to use relatively thin wings. That is, wing sections with maximum thickness small compared with width or chord. The thinner the wing, the less the air is speeded up, and so the critical Mach number is raised. These two wings are of the same general shape and at the same angle of incidence. The tunnel speed is the same for each. As it increases, The shock wave forms on the thicker wing at a Mach number of 0.8, but not a sign yet on the thinner one. Here it comes at last, at a Mach number of 0.9. But wings can't be made too thin, or the landing speed would be too high. The other important way of raising the critical Mach number is by the use of sweep back. To understand this, let's look from above at the flow over a wing. The contour of the wing section determines the amount the air is speeded up. Now sweep the wing back. We can represent the velocity of the airflow ahead of the wing by an arrow of a certain length. We can consider this velocity as made up of two smaller components. A yellow component at right angles to the leading edge, and a red component parallel to the leading edge. The red component can be considered to flow along the span and is not speeded up by the wing section. But the yellow component flows across the section and is speeded up by it. It is therefore only this component which affects the wing's critical Mach number. So the maximum speed reached over the swept wing will be less than it would be over a similar straight wing. In particular, if the flow over the straight wing has reached the speed of sound, at the same flight speed, the flow over the swept wing will still be subsonic. The swept wing has therefore a higher M crit. The greater the sweep back, the more the critical Mach number is raised. For instance, suppose the straight wing has a critical Mach number of 0.8. By sweeping the wing back to 35 degrees, the M crit is raised to 0.98. But this is only the theoretical result for an infinitely long wing. In practice, the critical Mach number would only be raised to about 0.9. Sweep back, like thin wings, brings its own problems at low speeds, such as tip stalling. So designers must compromise between high speed and low speed requirements. And aircraft designed to fly near the speed of sound use thin wings together with sweep back to obtain a high critical Mach number. If the swept wing is too thin to contain the engines, they can be mounted externally in pods. All these improvements in design are reducing shock stall troubles in the difficult earlier part of the transonic range. Still, faster flying is only possible when wave drag can be reduced. The drag caused by the shock waves changing kinetic energy into heat. A new design principle helps to do this. Area rule. Consider this aircraft. Take a section through it at right angles to its axis. So, represent the cross-section on a graph. Do this at points all along the axis. The resulting curve is irregular. Let us redesign the aircraft to smooth out the bumps in the curve so that the cross-section area changes gradually and not abruptly. So instead of the curve with bumps, a much smoother curve is obtained. This means the fuselage must have a waist to compensate for the wings and must flare out again behind. Above Mach 1, the bow wave adds its own drag. This can be reduced by having leading edges, nose, sharp rather than rounded. Compare the effect on the bow wave of sharp and rounded leading edges.